Okay, so what we're talking about now is rational functions. And so in general, what we're talking about is like when x is in the denominator, like you have 1 over x, that graph would be like this. You could have negative 1 over x, which is the other two. You could have 1 over x squared where both are going up, like that. And you could have negative 1 over x squared where both are going down. What you'll notice about this is, at least for these two functions, they're in diagonal quadrants. They're symmetric to the origin. Symmetric to the origin. Which means they're odd. They're odd functions. As opposed to these two, which are symmetric to the y-axis, which would be called even. Okay, it's not just because it's an exponent of 2, because we've talked about other types of functions being odd and even also, but like, for example, the absolute value function would be even because it's symmetric to the y-axis. So it's not just based on some exponent. It's that it's symmetric to something. All right. Now, what you could notice about this, and some of this you learned in Algebra 2, is that, let me emphasize this first one. You have vertical and horizontal asymptotes. Vertical and horizontal asymptotes. So this one has a vertical asymptote at x equals 0 because it's not shifted left or right any. And this one has a horizontal asymptote at y equals 0. Horizontal asymptote at y equals 0. And then from there, I'm going to start going through these notes. Any questions before we really get started? Okay. So your objective is to be able to find the domain of a rational function. What you'll notice is that the domain is going to be related to the vertical asymptote. I'm actually going to put that related to the vertical asymptote. So if you have a vertical asymptote at x equals 0, then the domain is going to be all reals x not 0. So if you have a vertical asymptote at 0, it's defined for every other value. And so your domain is not going to include where your vertical asymptote was. Okay? Questions? All right. Then be able to locate the vertical asymptotes and your horizontal or oblique. So those are your objectives. Now, on what I'm using right now, these have your blanks in bold, like when we get to here. While we're studying this, integers are positive or negative whole numbers. So whole would be a blank on your paper. They're not decimals or fractions. Ratios of integers are called rational numbers. Ratios of integers are called rational numbers. So the reason why we're talking about integers and rational numbers is because sometimes on your instructions on your Math Excel, it says answer in the form of an integer. So if you had like a half or a third, that's not an integer. So we can't do it like with fractions. An integer would be a whole number that's either positive or negative, and also includes 0. They're not decimals or fractions. Ratios of integers are called rational numbers. Like, it says it includes all integers plus fractions like 3/5, decimals like 0.6, also repeating decimals like 0.3 repeat, which is 1/3. It doesn't include square roots like square root of 5 that has a decimal and goes to the end of the calculator screen without repeating or not repeating. So a great example of irrational numbers are all your square roots, that don't end up being whole numbers. If you have a square root of 9, that does reduce to 3, so that's still rational, and that's still an integer and a whole number. But if you have square root of 5, it's random. Okay, it's not repeating. Another great example of a rational number, an irrational number would be pi. So those are examples of irrational functions and irrational numbers. Recall we've recently studied polynomials. Ratios or fractions of polynomials are called rational functions. Any questions? Are you up here?
Yeah.
Okay. Okay. So then for your notes, for the first one you have a definition. A rational function is of the form p of x over q of x, where p and q are polynomial functions. And it's not the zero polynomial, which is just when it's zero. The domain is all reals except for when the denominator is zero. One of our ways we're going to do this is we're going to set our denominator equal to 0 and solve. And then from there figure out, where our poles or asymptotes may be. Okay? So our definition is if as x approaches some number c, the values with the absolute value of r of x going towards infinity, then x equals c is a vertical asymptote. Notice that it's x equal because vertical lines are of that form where it's x equals some number. And if it's the y-axis, that's x equals 0. The graph of R never intersects a vertical asymptote. Never intersects a vertical one. Okay, questions? Okay. Looks like we need to do more of this tomorrow. So this is kind of like a good stopping point. We just got 1 or 2 minutes.